This is CBS Eye on the World. I'm John Batchelor. Hotel Mars, Episode N. David Livingston, Dr. Space himself of the Space Show, is here as my colleague and co-host, and we're zooming to the cosmos. We welcome Dr. Marcel Pawlowski of the Leibniz Institute for Astrophysics Potsdam. He is the Leibniz Junior Research Group leader, and in Science magazine, which is the peer-reviewed top of the pile for America, opposite Nature in Europe, we read that Marcel and his colleagues have solved one problem and created another in the cosmos, and that's a good thing. When astronomy creates problems, it means we're learning. And the problem goes this way. There were once too few dwarf galaxies for the standard model. Now, thanks to Marcel, there are too many. So let us recover what was wrong when there were too few. What is a dwarf galaxy? And then we'll go to the too many part. Marcel, congratulations and good evening. And this is wonderful. What does it mean to be a dwarf galaxy? It's charming, you know, the seven dwarfs. And what does it mean that we were worried that there were too few? Good evening to you, Marcel.
Hi, good evening to you too, and thanks for having me. Let's start right with your question, dwarf galaxies. If we think of galaxies, we usually imagine these grand spiral galaxies like the Milky Way, but they are surrounded by much smaller objects, so-called dwarf galaxies, which have only maybe down to a few million stars or even fewer. And usually, well, one galaxy like the Milky Way is surrounded by many of those. They are predicted to be very numerous. So in the 1990s, 1999, first computer simulations of cosmological structure formation. So they take the early universe distribution of dark matter and evolve it forward and predict how many galaxies there should be today. They predicted that a galaxy like the Milky Way should be surrounded by hundreds of little dwarfs. At that time, we only knew of 11. So there's a major discrepancy. So that was termed the missing satellites problem. So the fact that the model predicts many more satellite galaxies than predicted.
So there were too few in the 90s, and here we are in the 20s. What's happened? What have you done?
So it's of course not me personally. It is a huge research field. So there has been a lot of progress on all fronts since the 1990s. So one is, of course, these computer simulations. The predictions have changed substantially. So initially, these computer simulations were very simple. They just assumed the so-called dark matter, which makes up 85% of the mass in the universe. So initially, simulations only considered that. But that also means that all the galaxies in those early simulations are dark. They are just little blobs of dark matter surrounding bigger blobs of dark matter that would host the Milky Way. Now, inside of those, you still have to form stars to be able to see anything, to really have a galaxy that we can observe. And that's a process that is can now also be modeled. So you have so-called hydrodynamical simulations where you model the gas infall into this dark matter cloud. You form stars out of the gas, and the stars go supernova and maybe expel the gas. So there's a lot of processes you can now model, and that shows that not all of these little dark matter clumps actually host a galaxy. So the predicted number of luminous galaxies has gone down a lot. At the same time, there's been observational progress. So in around 2005, the Sloan Digital Sky Survey started to expand the knowledge of the Milky Way satellite galaxies, for example. So where we had known 11, this number doubled within a few years. So there have been additional discoveries just on the observational side. So in addition, there are other ideas how to address this discrepancy in the numbers. So you could modify the type of dark matter. You assume the standard model of cosmology assumes so-called cold dark matter, so rather slow dark matter, massive dark matter particle that moves rather slowly compared to the speed of light. So it can form very compact clusterings and clumps. But you could also say maybe dark matter is warm, so it's moving a bit faster, and that washes out the smallest structures. So you would have less predicted satellite galaxies. So yeah, there were many ways of addressing this problem. So I think most of us astronomers have considered that solved because, well, we can get rid of many of these predicted satellite galaxies to match the number that was known.
David, you have a question for Marcel.
Yeah, Marcel, nice to meet you. Do all astronomers use the same simulation models, or are there different ones out there? And what kind of confidence interval do you guys work with for these models? What level of accuracy do you give them for being correct? Because if they're not correct, then your research that follows has errors in it too.
Absolutely. So there's the good thing is there's a lot of different simulations that use different prescriptions, different parameters. One issue, of course, is that processes like star formation, you cannot resolve in sufficient detail to actually form single stars in your computer simulation if you at the same time want to model a whole representative volume of the universe. So you always make simplifications. It's called subgrid physics. So it's physics that's happening below the resolution limit of your actual simulation. So that means you have to make certain assumptions. You have certain pre-parameters you can tweak. So there are different approaches to this, and different simulations therefore also give you slightly different numbers. But what we also do in our research is not just compare to these simulations, but also more to theoretical models of how many galaxies or satellite galaxies there should be at a given mass. So you have different approaches, and they are broadly consistent with each other, but that doesn't necessarily mean that they are correct.
Marcel, I love the idea that I've learned something from you already. Slow dark matter. Wow. Wow. That is a use of an adjective that opens up everything I've learned about dark matter now has to be reconsidered. What the heck is slow dark matter?
Well, if you assume that dark matter is a new elementary particle, that particle has a certain mass. And if it's very light, like a neutrino, for example, it would move with almost relativistic velocity, so almost the speed of light. That would mean it kind of washes out everything, all kinds of structures on small scales, well, small for astronomers, of course. So like galaxies, it maybe form galaxy clusters, but not something like the Milky Way or a satellite galaxy. The opposite end is so-called cold dark matter, which is a very massive particle that is therefore moving very slowly compared to the speed of light. For the Milky Way, it would still move with hundreds of kilometers per second, so it's actually pretty fast for human standards, but for astronomers, that's slow. And because it's so slow, it kind of gets stuck in small structures as well and can therefore form many, many little clumps.
So the image that I have of dark matter has to be adjusted. It's not the missing matter that holds the Milky Way together. It's a library of different kinds of dark matter. Is that how to now think of it?
No, I mean, the general concept of dark matter is that it holds the Milky Way galaxy together, or also other galaxies, of course. But there are different ways of interpreting this. So different kinds of or types of dark matter that could be realized in nature. So it could be this cold dark matter, it could be warm dark matter that's moving a bit faster. And then there are also other alternatives. In principle, you could even say it's a mixture of them, but that is scientifically not too convincing because we kind of want to keep our models as simple as possible and not introduce many more unnecessary parameters.
David, you have a question.
Another term, what is primordial magnetic field, and what is the relationship of that to your work on dwarf galaxies?
So magnetic fields are one of those additional components you can nowadays model in computer simulations, and they have an effect on how galaxies form and evolve. So again, this is in a sense subgrid physics and an additional complication to those simulations. But this can affect how many luminous galaxies you form and predict in your model.
You used the Subaru Telescope, where a team used the Subaru Telescope in Hawaii for studying these galaxies. The article in Science magazine points to the future, where you're going to have access to the Vera C. Rubin Observatory that they're constructing in Chile. What will that allow you to do that you can't now do? Is it better, faster? As I understand, Vera C. Rubin is about taking a map of the whole sky.
Yes. So Well, I didn't use the Subaru Telescope. That's a group in Japan who discovered a surprisingly high number of satellite galaxies of the Milky Way using Subaru in a very small patch of the sky. So about 2 times as many than expected. For the Rubin telescope, yes, that will cover a large portion of the sky with very deep observations, which means they will discover a lot more satellite galaxies around the Milky Way. So we will get a much more complete census. The dwarf galaxies and the satellite galaxies of the Milky Way we know nowadays, there's, for example, a bias that they are relatively nearby because it's easier to find it if it's close to us. With the new observatory, this boundary line will be pushed to much larger distances, and that will also tell us something about the radial distribution of these galaxies, which can in turn then also give us constraints on the models. So that's for the Milky Way, right? And then, of course, you also would like to study this beyond the Milky Way for other host galaxies, like the Andromeda Galaxy or even more distant ones, which is where our work comes in mostly.
David, you have a question.
Yeah, so I'm wondering if your model and your research applies to distant galaxies, such as a spiral galaxy or Andromeda. Is it universal, or would there be different rules for those galaxies?
Yeah, I mean, that's basically the point of our research now. So we had this missing satellites problem. We have a number of solutions to reduce the number of predicted satellite galaxies, which made it match with the number of observed galaxies. Now, that was all kind of tweaked to reproduce the Milky Way or the local group. With our new research, we look at much more distant galaxies, up to 150 million light years away. And we look not just at the single one, but we look at the whole population of about 50 host galaxies. And if you look at those, you count all the dwarf galaxy candidates around them, you find about 10 per host. And if you compare that to the models, you would expect only 3. So suddenly we have this mismatch. So for the Milky Way, it kind of matches. Outside of the Milky Way, now it doesn't match, but a cosmological model or simulation should reproduce the whole universe, not just a small patch of it. So that's actually the problem. We cannot tweak the model to match one or the other. We need to find a model that matches all of the observations at once.
Let me see if I can summarize before we give you a big budget. There was the perception that there were too few dwarf galaxies. And then there was the perception there were too many dwarf galaxies. This is for the Milky Way. However, your model now tells us there's just the right amount. It's beginning to sound like the 3 bears. There's just the right amount of, is that just the right amount now, thanks to your model? Is that correct, Marcel?
No, I think right now we kind of oversolved the problem. So we have reduced the predicted number so far that it's now below the observed number if you look outside of the local group, outside of the Milky Way. And so in the universe, in a broader scale, we now seem to have the opposite problem of what we had at the beginning.
We're now about to turn to the possibility that Marcel has an unlimited budget, which is the dream of all astronomers. So Marcel, tell David and myself, what are you going to do with your money?
Well, there's a very attractive scenario, of course. I think I would have two answers. One is kind of the obvious one. So we need more data. We really want to understand the universe better. So it would be nice to focus on discovering more dwarf galaxies around distant hosts down to very, very faint luminosities for the dwarfs, which means very deep observations. So something like Nancy J. Gray's Roman Space Telescope is coming up. Lots of observing time with that to really find all the faintest dwarfs. And then also, once you found them, you need to follow up. You need to know their velocities. You need to know their distances. So for all that, you would, again, like to have additional observational data. So we have made very good use of the MUSE instrument on the European Southern Observatory's VLT. So that would be, well, if I have unlimited budget, I would like to buy my own and just target lots of dwarf galaxies. So that's one half of the answer. The other half would be, I think we also need theoretical progress, and this kind of research where they have many different alternatives being proposed to a standard model would benefit from kind of a research institute where you can give young minds the opportunity to study different alternatives in a very parallel way. So giving them job security for longer terms than the typical postdoc position, which is 1, 2, 3 years, something where you can really focus on long-term comparisons of models would be, I think, a very attractive way of spending my unlimited money.
So the dwarf galaxies become a school. Wonderful. David, you have a question about the dwarf galaxies.
What about using space telescopes like James Webb or Hubble? Do they add to your capability to get data?
Yes, absolutely. So Hubble is excellent in resolving dwarf galaxies, even beyond the local group, if you have enough time. So you can use it to measure distances, which is important because if you want to study dwarf galaxies around distant host galaxies, you might discover a candidate, but you don't know whether it's actually a dwarf belonging to this host until you have measured distance. And for that, you need something like Hubble as a follow-up. Or the Roman Space Telescope, which is coming up in a few years, which has a much wider field of view, but similar resolution to Hubble would, I think, also help a lot. And then in addition, spectroscopic follow-up is also really important. You don't need a space telescope for that, but you need a very big telescope. So you need one of those, 8-meter or larger to really catch enough light of a dwarf galaxy to be able to measure the spectra of these really faint distant stars and determine how it's moving, how fast it's going.
Marcel, again, I want to summarize what I learned from you about how you will spend the money. You would like teams working on all the alternatives simultaneously because you don't need to commit to one or get one done. And so that could go on indefinitely. Is that the way astronomy is done these days? You say, all right, team, you go this way, we'll go that way, and we'll see what we come up with. Is that how you think of astronomy?
I think that's not done enough. That's why I would like to use the money to do something like this. Because when you study different alternatives in parallel, first of all, you come up with questions that you might not ask otherwise. And secondly, you can actually say, what model does predict what, and how can I make observations? How can I design my observations to discriminate between them, to then rule out certain models? So the goal is not to indefinitely study all these models, but to study them on an equal footing and then really decide which ones can we rule out. And that way we would make a lot of progress, I think.
The joy of this, David, is that Marcel's at the frontier. David and I so much enjoy as amateurs, Marcel, listening to what the edge of knowledge is. And I think, David, do you agree we just learned it?
Yes, of course. I think it'd be really exciting.
David Livingston, Dr. Space, my colleague and co-host, and we've just been to the end of knowledge and come back thanks to Dr. Marcel Pawlowski, Leibniz Junior Research Group leader at the Leibniz Institute for Astrophysics Potsdam. This is CBS Eye on the World, Hotel Mars. I'm John Batchelor.